Hello everyone, myself Dr. Doma Sree Lakshmi, Assistant Professor in the Department AIML, Institute of Aeronautical Engineering. In this lecture, the topic is on graph terminology, induced subgraph, spanning subgraph, complement, complete graphs, and bipartite graph. This lecture will have a discussion on these topics. In graph terminology, the first we discussed about graph, and now we are going to discuss the subgraphs present in the graph, which are subgraphs, induced graph, and spanning subgraph. So here is a definition. A subgraph H of a graph G is a graph where H contains some of the edges and vertices of G. That is, the vertices of the subgraph belongs to or subset of the original graph, and the edges of the subgraph or subset of edges of the main graph. So this is the subgraph simple definition, and if you go with an example, then here is an example. Consider the graph G below. Find two subgraphs of G, both which have vertex set V, A, B, C, F, G, I. So in this figure, they are asking two subgraphs which includes few vertices. So we will see here the induced subgraph with the vertices A, B, C, I, G and F. So this is the induced subgraph in the main graph. So the vertices A, B, C, I, G, F are subset of the main graph. And one more graph is spanning subgraph. So even this subgraph should have the vertices A, B, C, I, G, F. So this is the spanning subgraph where A, G, F, B, I, C are subset of the main graph. So here we will see the definition. The graph shown on the left above is a special type called an induced subgraph, since all edges are present between the chosen vertices. And second one, a special type of subgraph called spanning subgraph induced all the vertices of the original graph. So spanning subgraph, induced subgraph are the two subgraphs which are in the main graph. And here, if we see a graph with vertices and edges are given, an induced subgraph is a subgraph G of V dash where V dash is subset of V, and every available edge from G between the vertices in V dash is included. We say H is a spanning subgraph if it contains all the vertices but not necessarily all the edges of G. This point we need to remember. when we discussing about spanning subgraph, we need to remember not necessarily all the edges are required. See, if 10 edges are there in the first graph, the subgraph, that is the spanning subgraph, may not have all the edges. It's not compulsory to connect all the vertices. Only few required edges are enough. So here V of G is equal to V of H, and E of H is subset of E of G. So here H3 is induced subgraph, and H4 is spanning subgraph. In these two subgraphs, there is no compulsion to maintain a set of vertices. They included all the vertices that belongs to the original graph. But here they are mentioning with one subgraph, that is one induced subgraph and one more induced subgraph. And similarly, here is a spanning subgraph. So, and the next topic is graph, how and when we will say a complete graph. A simple graph G is complete if every pair of distinct vertices is adjacent. The complete graph on n vertices is denoted as k suffix n. Here we will have few examples. Here only one vertex is there, and this is a complete graph or a simple graph. Here there are no connecting edges because only one vertex is present. And example 2, here we are having two vertices A, B, a connecting edge E1. Now, this is a complete graph. Why? Because A is connected to B and at the same time B is connected to A. Example 3. Here three vertices are there, A, B, C, and edges E1, E2, E3. Now, vertex A is connected to B and C. Vertex B is connected to A and C. Vertex C is connected to A and B. This means when we will tell the given graph is a complete graph means every pair of distinct vertices is adjacent. So for vertex A, C, B are adjacent. For B, AC are adjacent. And for C, AB are adjacent. So now this is a complete graph. Similarly, here four vertices are there, A, B, C, D, E1, E2, E3, E4, E5, E6. 6 edges are there. But for A, the adjacent vertices are B, C and D. So A is connected to all the other three vertices which are adjacent to that A vertex. Similarly, B is connected to the rest of three vertices A, C, D. And C is connected to the adjacent vertices B, D, A. So this is said to be a complete graph. So here are few more examples. Example 5 and example 6. If you analyze this, vertex A, B, C, D, E. So now if you check, this A is connected to B, C, D, E. So A is connected to 4 vertices. Similarly, B is connected to 4, C is connected to 4 vertices, D is connected to 4 vertices, and E is also connected to 4 vertices. So this is also a complete graph. And even here, A, B, C, D, E, F, 6 vertices are there, and each vertex is connected to the rest of the 5 vertices. A is connected to the rest of the 5 vertices, B is connected to rest of the 5 vertices. So this is also a complete graph. And next topic is properties of this complete graph. Here, few properties are there. First one, each vertex in Kn has degree n minus 1. Example, here I am taking a graph which is having 3 vertices A, B, C and edges E1, E2, E3. Since this is a simple graph, we can tell 3 edges are there or 3 connecting lines are there. But if there are more number of vertices, say n is equal to 50 vertices, then the edge connections we will need to be identified. So here what we will do is, how many edges are there and what is the degree of that, we can find out simply by using these 2 formulas. One is, to find out the degree, we will use n minus 1, and to find out the edges, we will use n into n minus 1 by 2. So this is the formula. By using this formula, we will find out the number of edges. And for this simple example, the degree of vertex A is 2. How we are identifying that? By using the formula n minus 1. For this simple graph, the n is 3. That is, the vertices are 3. Now 3 minus 1 is what? 2. So each vertex will have the degree of 2. And this property is only for a complete graph. And here for B, the degree is 2. And for C, the degree is 2. So if we go for the second example where n is equal to 50 vertices, now how to identify the degree of each vertex and how to represent the edges. So for this purpose, we will use these formulas. N minus 1, the degree is equal to n minus 1. That is 50 minus 1. That is 49. So, and vertices with 50 has a degree. Each vertex degree is 49. And similarly, if you want to find out the edges, then the formula is n into n minus 1 by 2. So here n is 50. So 50 into 50 minus 1 divided by 2. So which is 50 into 49 by 2. So how we will calculate here? So 25 into 49. 9 2s are 18, 22, 4 5s are 20, 4 2s are 8, 9, 10. So in this way, simply we can identify number of edges. If 50 vertices are there, by seeing the connecting lines or by seeing the edges, it is not possible to identify. So with this formula, n into n minus 1 by 2, we can identify number of edges required for that complete graph. So this is the first property where degree is calculated through n minus 1. And second property, edges we need to find out. And last one, the Kn contains the most edges out of all simple graphs of n vertices. So these are the 3 properties where we can use for complete graph. And next is click size. What is a click and how to identify this click size? That is based on the definition, how we will see the click size of a graph W of G is the largest integer n such that kn is a subgraph of G, but kn plus 1 is not. So simply, in other terms, we can say the largest complete graph that appears as a subgraph. The largest complete graph that appears as a subgraph. This is called click size of a graph. This is called click size of a graph. So here a graph is there. We will identify the click. Or even we can see the size of the click. So we will first assign the vertices A, B, C, D, E, F, G, H. So vertices 1, 2, 3, 4, 5, 6, 7, 8. 8 vertices are there. 8 vertices are there. And now the edge connections, we will start from E1, E2, E3, E4, E5, E6, E7, E8, E9, E10, E11, E12, and then E13. So already from C to D is given, C to E is given, C to H is given, C to B is given. Similarly for D, D to C is done, D to E is done, D to A is done. And now for E, E to A is done, E to 9 is done, E to C is done. For F, F to A is done, F to G is done, F to E is done, G to H is done, G to F is done, and H to A is also done. So totally 13 edges are there. Now my concern is I need to find out the click in this graph. So it is a subgraph, and moreover each vertex should include all the adjacents. So please look here. I will separate the subgraphs in this. So A, C, D. So A to C, C to D, and D to E, E to A. So this is one subgraph. But A is connected to D, and D is connected to A. E is connected to A, E is connected to D, and E is connected to C. If you observe carefully, here A to C, fine. Next A to D, next A to E. Similarly, A is connected to C, D, E. Similarly, we need to check C also need to be connected to A, D, E. So now C is connected to D, C is connected to E, and next we need to check even D is need to connect with A, C, E. So D is connected to C, D is connected to A, and D is connected to E. And now fourth vertex E. E is connected to A, E is connected to D, E is connected to C. So here this is a subgraph, and where the size of this is 4. Because A, C, D, E are connected to each other. These are connected to each other. This is known as click, and the size of this click is 4. Because A is connected to the rest of the 3 vertices, C is connected to the rest of 3 vertices, D is connected to rest of the 3 vertices, and similarly E is connected to rest of 3 vertices. So if you draw this graph, induced graph or a subgraph, A, C, D, E, which is connected to A, and now please we will connect this all together. See, now the degree of A is how much? 3. The degree of C is how much? 3. Degree of D is 3. Degree of E is 3. So now this is a clique where the size of this clique is 4. Similarly, we need to identify the cliques. If we come to this example 2, consider this vertex A, B, C, D, E, F, G, H. So these are the vertices, and here A is connected to D, A is connected to C, but F is connected to A, not with D. There is no connecting line or edge between F and D. So this is not a clique. This is not a clique. So observe carefully. Here few vertices are there. If you take this as a subgraph, A to D, A to E, then D to E, E to F, consider this as a clique. But as per our definition, A should connect to D, F. It is there. F should connect to A and then D. But there is no connecting edge from F to D. So this is not a clique. And the size of the clique is not able to find out. So if you go with any other induced graph also, any other subgraph also, there is no connection or there is no edge between the rest of the vertices. See, A to H, H to D, G to F, fine, and F to A, this is fine. But H is not connected to F, so where a clique is not possible. So this is about clique and clique size. And now the next definition is complement. As we know, complement, if we write 1, then the complement of 1 is 0. If we go with 0, then the complement of 0 is 1. This is general discussion where we know already. Now we will see complement of a graph. Here the definition is a simple graph G is equal to V, E. Define that the complement of G as a graph G is equal to V, E, where an edge xy belongs to E if and only if xy does not belongs to E. That is, please look here. This is a graph with vertices A, B, C with edges E1, E2, E3. So now the complement of this graph is, according to the definition, wherever the connecting edge established, we need to remove that edge connection. So that is the complement of the given graph. Now A, B, C, 3 vertices are there. As if you observe, a connecting edge is established between A and B, B and C, C and A. Now we will remove that. We will remove that A to B, B to C, C to A. This is not required because this is complement. So this is complement of, the figure is complement of this one. And second, example 2. Here 4 vertices are there, A, B, C, D. Now the complement of the given graph. We will take the vertices A, B, C, D, and now we will analyze. A to B, a connecting edge is there. We should remove that connecting edge. We should not draw that connecting edge. A to D, there is no connecting edge, so we need to connect these 2 vertices. A to D. Fine. Next, D to C, there is a connecting edge. Now, here, there should not be a connecting edge. Now, B to C, there is no edge connection. So, here, we should draw that edge. Now, B to D, there is no connecting line. So, here we won't draw A to C there is no connecting line, so we will draw this. So wherever edge connection is there, we should remove. When there is no edge connection, then we should establish a connection between the vertices. So this is example 2. Complement of the given graph. So if you move on to this graph, A, B, C, D, E, F. 6 vertices are there. And edge connections are also established for few vertices. Now we will draw the complement of the graph. Now A, B, C, D, E, F. Now A to B there is no connecting line. So we will maintain or we will establish the edge connection. Next, B to C there is an edge connection. So we will remove that. C to D there is no edge connection. So we need to establish that edge connection. Now D to E there is edge connection. So we should not maintain the connection. Now A to E connection is there, not required. E to F connection is there, not required. A to F connection is there, not required. Now we need to check wherever the connection is not there, we need to establish. First, initially I am going to take A. A is connected to B? No. So we connected here. Now A is connected to C? No. So we need to connect. Now A to D connection is there? No. So we need to establish. Now A to E is there? Yes. So not required. A to F is there? Yes. Here not required. Now coming to the vertex B. B is connected to C. So we removed that connection. B is connected to D? No. So we need to maintain the connection. B to D. Next, B to E is there? No. So we need to establish. Now, B to F is there? No. So we need to establish. B to A is there? No. So we already established B to A. Next, B to F is there? No. We established. This is related to the vertex B. Now come to vertex C. C to D is there? No. So we established C to D. Now C to E is there? No. So C to E we need to establish. Next, C to F is there? No. So C to F we established. Next, C to A is there? No. So we established C to A. Next, coming to the vertex E. E is connected to D. So we removed that. E is connected to A. We removed that. E is connected to F. We removed that. Now E is connected to B. No. Here we established a connection. Now last vertex. F is connected to A and E. So here we removed F to A and F to E. But it is not connected to B, C, D. So here we established connection to B, C and then E and then T. Fine. So this is the complement of figure 3. This is complement of figure 3. So in this way, when a graph is given, the complement graph we will establish. We will design. So here are the output for that. And next concept is bipartite graph. So a graph G is bipartite if the vertices can be partitioned into two sets X and Y, so that every edge has one endpoint in X and the other in Y. Then we will say it is bipartite. Bi in the sense two. So here X is one set and Y is second set or another set. If we have n number of vertices, if you are able to split into different sets, then it is said to be k-partrite sets. K per tight. Number of sets. Based on the sets, we will represent as K per trait or bi per trait. Fine. So now we will see how we will separate two sets, X and Y. So here is a graph. Here is a graph where the vertices A, B, C, D, E, F, G. In this given graph, A, B, C comes under set 1. A, B, C comes under set 1. And for set 2, D, C, F, G. For set 2, D, C, F, G. And what it is saying? The bipartite graph, what it will say is, two sets it will establish X and Y. And now, it will establish the relation between different types of objects. It will establish the relationship between different types of objects. And if you see, A is connected to D, A is connected to E, and then B is connected to D, B is connected to E, B is connected to F, and B is connected to G. So each vertex of set 1 is connecting with the vertices of set 2. And in set 1, C is present. This is connected to D and then F. So in this way, we will separate the vertices into two sets, set 1, set 2. So wherever the connection is developed or the relationship is developed, then we will assume that there are two sets. So we will allot all the vertices to two different sets. Here A, B, C comes under one set, D, C, F, G comes under one set. Because A is not connected to B and B is not connected to C. So it means A, B, C are belonging to only set 1. And here D is not connected to E, E is not connected to F, and F is not connected to Z. So these four vertices comes under one set. This is set 2. So finally we can say that if there is any relationship between vertex of first set to the vertex of another, then that belongs to the set 2. Fine. So this is bipartite. And next, one more point is there, that is complete bipartite. Next definition, complete bipartite. This means, in previous example, A is connected to only D and E. A is connected to only D and E, but not with F, G. There is no connection between F and G. Right? And even C is connected to only F and E. Example, F and E, but not with D and G. But we are saying that they are bipartite. That is bipartite graph. And the next concept is complete bipartite. Here, each vertex of set 1 should connect with all vertices of set 2. Each vertex of set 1 should connect with all vertices of set 2. So this is A, B, C, D, E, F. So A is connected to C, D, E, F. Right? B is connected to C, D, E, F. So set 1 includes A, B vertices. Set 2 vertices C, D, E, F. So the way which they are connected, based on that, two sets are separated. And now, so example 2, here the set 1 consists only one vertex A But set 2 consists of 3 vertices. How we are telling? Based on the connection established or based on the relationship established. A is connected to B, C, D. So this is complete bipartite. So simple. Every vertex of set 1 need to be connected to all the vertices of set 2. Every vertex of set 1 need to connected with all vertices of set 2. Then it is said to be complete bipartite. It is said to be complete bipartite. When a graph is given, say like this. If they ask to split that graph into 2 sets, then the vertices are need to be separated, right? So here set 1 consists of only one vertex, whereas set 2 contains rest of the vertices. Assume that this is 1, this is 2, 3, 4, 5, 6, 7, 8, 9. So if set 1 contains only one vertex, rest of the vertices, that are 8 vertices, belongs to set 2. Because 2, 3, 4, 5, 6, 7, 8, 9, they are not connected with each other. They are connected to only one vertex to number 1. So that is set 1, which is having only one vertex. Set 2, 8 vertices. In this way, we can separate 2 sets. So bipartite, complete bipartite. And the next topic is k-partrite. Here, based on the number of sets, here the k-partrite will be analyzed. This is set 1, may or may not contain n number of vertices. If at least one vertex is established, then it comes under set. This is set 2, assume, and this is set 3, and this is set 4. Okay, this is a k-partrite. And here, if you observe, this is set 1, and this is set 2, and this is set 3. Here, set 1 vertex is connected to all vertices of set 2. And at the same time, set 1 vertex is connected to all vertices of set 3 also. And set 1 vertex B similarly connected to all vertices of set 2 and all vertices of set 3. So this is complete k-partrite. Complete k-partrite. And this is partrite, k-partrite. In number of sets, 4 sets. Fine. So this is isomorphic. So with this, the lecture is done. Thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.